This is going to be a video going through some of the topics that you're going to find in Chapter 1 is on physical properties. And those are things that describe a substance, and you can observe those without actually changing the substance. So the color of something, what the mass would be, the density, the state of matter, the temperature, just things that we could see without actually changing the substance. And so here would be several examples that you can see in your book of physical properties. Chemical properties, on the other hand, are properties that we can only see when it changes into another substance. For example, if it's going to be flammable, if it tarnishes, if it's toxic. Those things we can't readily see. We only can look at those when it's actually going through a change. Now, a physical change is one in which just the physical properties are changed. It doesn't actually make it into something new and different. So freezing, melting, coloring something, cutting it in half. Physical changes can be easily reversed. Example, if we cut something in half, we could put it back together. If something melts, then we can refreeze it. So those should be things which you could go back and forth between. A chemical change is something, though, that changes it into a whole new substance that you can't go back very well. So water freezing into ice, we said that's easily reversible because I could take the ice and melt it. If water evaporates, then I could simply condense it. If butter melts, then I could just make it back into a solid by letting it cool. A bicycle left outdoors begins to rust. I can't really get rid of the rusting process. It's not reversible. I can't change it back to what it was. Sugar dissolves in hot coffee. Well, in that case, all I have to do is let it evaporate and I could get the sugar back out. But the bicycle rusting is the one that's chemical because it made it into something new and different and I can't go back. When we talk about matter, we have two basic categories. We have substances or we have mixtures. Mixtures are things that are just mixed together. Substances are things that have undergone chemical changes. So a mixture would be like I can mix carrots and celery and lettuce in a dish together to make a salad. Or if I take sugar and mix it in with salt. Or if I have sugar dissolved in water. That would just be something that's mixed together. If all the things look the same, then it's homogeneous. So in this case, this is an alloy and we can see it all looks the same. Heterogeneous means I can see differences in the particles. So in this case, this mixture where it's all mixed together, those look different. So in my salad example, that would be heterogeneous. Homogeneous would be salt dissolved in water because I can't distinguish the salt from the water unless I add so much that it settles. But homogeneous meaning all look the same, hetero meaning look different. Now on the other side of this, a substance has gone through a chemical change and it can either be an element or a compound. Now all elements are going to be found on the periodic table of the elements that's in the front of your textbook. A compound means we have two or more elements that have been chemically combined. So when we think about sugar itself, it is made up of carbon, hydrogen, and oxygen, and it's all chemically combined, and it can't be separated physically. I can't sift it or evaporate the water or anything like that that's going to change it back. So it's gone through a chemical change and it's made something brand new and different. Alright, so this next slide just kind of talks about elements, how there's just one kind of atom, whereas a compound is two more atoms that have been chemically combined. And the smallest particle of that we call a molecule. Alright, the next section is going to be on measurement, and that's because we're going to be doing quite a bit of measuring in chemistry. So for every measurement, it has to have both a number and a label on that, or a unit. And we use some kind of a standard scale so that we can reproduce our measurements. But every one has to have both a number and a unit, because the number itself doesn't mean much. Alright, things that we could measure would be length, mass, time, temperature, etc. And they're going to tell me what the unit that I'm going to use is. For example, length is going to be meters, mass is going to be kilograms, time is going to be seconds, and then the symbol. So M for meter, kilograms for mass for kilograms, and S for seconds. We are probably not going to be dealing with electric current or luminous intensity. Alright, so our standard system of measurement is based on the metric scale, and those are things that are derived from those SI units that we saw on the slide before. If it's derived, that means it's a combination of units, like grams per milliliter, so it's got more than one. And I'm going to use metric prefixes like centi, kilo, in order to make that measurement fit. Alright, so here's some of our prefixes that we're going to use. We have our base unit, which sits right here in the middle, and then we have kilo, hecta, deca, deci, centi, milli on either side. And then if we need to get even larger or even smaller, we can do that. And you can see they're all based on 10. So in other words, if we have deca, deca means 10. So a decagram would be 10 grams. A decigram, in that case, would be 0.1 grams. And since it's based on tens, that means that we can just slide our decimal back and forth in order to convert units. And one of the videos that I have posted in this week's is all on metric prefixes and how to convert back and forth. Alright, next topic is density. And density is defined as the amount of matter in a given amount of space, or mass divided by volume. So the equation here is density equals mass divided by volume. And this has a unit, usually grams per centimeter cubed or grammed per milliliter. So it has grams, which is a mass unit on the top, and a volume unit on the bottom. And this is just, for example, the density of copper. And that would be a physical property. So we could do some problems. So this one says calculate the density of a metal sample, and they give me the mass and they give me the volume. So I'm going to use my equation, and then I'm going to plug in the mass that I was given and the volume. So I would take 18.96 divided by 4.31, and I get an answer of 4.40, and the grams was on the top and the centimeters cubed was on the bottom. And I could use this equation and rearrange it, for example, if I wanted to find the volume or if I wanted to find the mass. As long as I knew two of the pieces, I could find the other piece. Alright, in this one they want to know which one would have the greatest volume, and they have given me the densities of these substances. So I know that density is mass divided by volume. So what that tells me is that if I have a small density, that means I actually have a very large volume. So if I look through here and I find one that has a small density, this is the smallest one, which means it's probably going to have the largest volume. Alright, energy has two basic forms. It's either potential, which is stored, or we could have kinetic, which is moving energy. So a child on a bike would be kinetic. Potential would be like the energy that you'd find in a can of green beans, stored up energy. And heat and temperature have very distinct meanings. Heat is the energy that's transferred from an object that's at a higher temperature to an object at a lower temperature. And temperature measures the average kinetic energy. And remember, kinetic energy was moving energy. So temperature is measuring how fast the particles are moving. The faster they move, the higher the temperature would read. And we're going to use units like calories or joules to measure heat and energy. And a calorie is defined as the amount of heat required to change the temperature of 1 gram of water 1 degree Celsius, which is not very much. 1 gram is pretty small, and changing it only a degree isn't very much. And a calorie has a conversion factor to go between calories and joules. So 1 calorie is 4.184 joules. And this calorie is similar to the one that we use for our foods, except the ones that we use on our foods are actually large calories. They're kilocalories, which would be 1,000 calories. So the ones in our foods are actually kilocalories. But typically you're just going to see calories, which a capital C, and capital C means kilocalories. And it's somewhat confusing that way, but apparently they didn't think the average person could understand kilocalories. All right, so there's their capital C, and that would correspond to 1,000 calories or 4,184 joules. Right, when we measure temperature, so that was energy. Energy is measured in calories or joules, and we could use that conversion factor to help us convert. But when we measure temperature, we usually use things like Fahrenheit, which we're used to, or in science, we're going to be using Celsius on all of our things, and Kelvin we will be using in some of our gas law problems. So we can see that the boiling point of water on the Celsius scale is 100, and the freezing point is 0. So has nice reference points that are nice even numbers. Unlike Fahrenheit, 32 and 212, those are kind of random numbers. And then we have for Kelvin, the boiling point is 373, and the freezing is 273. And both of these have the same difference between freezing and boiling. So that means in order to convert Celsius to Kelvin is fairly simple. All I have to do is take my Celsius temperature and add 273. So here we have one where it's 37 degrees Celsius. I would add the 273, and you can drop the 0.15 if you want or leave it on, but if you add 273, that's going to tell me my temperature in Kelvin, which would be 310. All right, significant figures. These are things which are usually kind of confusing. So significant figures are going to tell me how well my device is measuring things. The more digits that it has on my device, or the smaller divisions that it has, the better the instrument is, and usually the more expensive. When I read measurements, I want to read the smallest markings on the tool, and then I want to estimate one more place, meaning one more decimal place. So I read the smallest itty-bitty markings, and then I have to estimate in between those little markings. And we don't do that on digital scales because obviously there's nothing that we could estimate. All right, so we're going to use significant figures whenever we are using anything that's measured. So this isn't things that we're going to count. These would be things that we measure with a ruler or something like that. And these significant figures are going to help us decide what is the best answer without providing any misleading information. So meaning it's going to tell them the smallest markings that I have on my tool. So it's going to tell me how well I can make that measurement. Now things that are exact numbers, these are things like that I can count. They have no uncertainty. They don't apply towards your significant figures, because if we say that we have 2 things, that's 2 with an infinite number of significant figures. So we don't count exact numbers for our significant figures, just measured numbers. All right, so for everything that I read, we always know there is some uncertainty. That last digit is the one that's uncertain. So in this case, I can see that this would be the 16, 17, 18. So my volume of water is somewhere between 17 and 18. Everybody could agree on that. We, however, would not all agree what this measurement is. And this one I can see is somewhere between 17 and 18, and I'm going to say it's a little bit more than halfway between the 17 and 18. So maybe I want to call it 17.6. However, somebody else could read it and say it's 17.5. And by the way, this dip in the water, the bottom of the dip is what we want to read, and that's called the meniscus. All right. In this case, we have a thermometer. We can read the 25, we can read the 30. Those are the smallest markings. Now in between there, I would say, okay, somewhere between 25 and 30, I would go halfway, and I would say that that would be 27.5. And I'm a little less than halfway, so maybe I'm going to estimate 27. So the 7 is the estimated digit, and that would be the one that not everybody would agree on. Everybody would agree that it's 20-something, meaning more than 25, but not quite to 30. But this would be the estimated digit. All right, when we round numbers for our significant figures, we, for example, count however many we have on the top. So this one has 3. And I'm dividing by a number that has 4 significant figures. So I want to use the least number when I report my answer. So if this one has 3 and this one has 4, the least amount would be 3. So I would round my answer so that I only had 3 significant figures. And just like in math, if it's 5 and bigger, I would round up if there was, a digit over here. So 23.8 has 3 significant figures. So the least number when I am multiplying and dividing. Now, scientific notation is a way that we can write really big or really small numbers. So we have a number between 1 and 9, and then it's times 10 to some power. So here we have a number that's written in scientific notation, and this means that it is moved 4 times. So the real number, if I take my decimal point, 1, 2, 3, 4, that means this is the actual number not in scientific notation. So a positive exponent is telling me that I'm going to move my decimal point to the right, which means I'm going to have a big number. If I ever have a negative exponent, that means I have a number that's less than 1. So positive exponents greater than 1 numbers. Negative exponent means my number is less than 1. So 8 means I'm going to move it to the left 8 times and have a number that is much less than 1. All right, unit conversions, we're going to use what's called the factor label method, meaning we're going to take our conversion factor and we're going to be able to cancel our units. For example, if I want to know to convert miles to kilometers or kilometers to miles, I can look up a conversion factor in my book. So it'll say 1 kilometer is 0.6214 miles, or 0.6214 miles is 1 kilometer. And then I'm going to use that conversion factor. So if I have 26.22 miles and I want to convert that to kilometers, I would take my conversion factor and I need to make it so that the miles is on the bottom and the kilometers is on the top. That way my miles cancel because one's on the top and one's on the bottom. If I started with kilometers, then I would want to take this conversion factor and flip it so that I had the kilometers on the bottom. So I'm going to line up my units and cancel. That's why it's called unit cancellation. So the miles cancel, and I would take 26.22 times 1 and divide by 0.6214. And that would give me 42.20. And this number has 4 significant figures, 1, 2, 3, 4. This number doesn't count because it's a conversion factor, so it's going to be an exact number, so I don't count that toward my significant figures. So since I have 4 to start with, that means I'm going to have 4 to end with. And that is pretty much the big stuff that you're going to find in Chapter 1.